Section 4.1, Systems of Linear Equations in Two Variables. First of all, we need to make sure we know what linear means. And again, with two variables, we're going to see x and y. But linear means you're going to have the variables having a power of 1. So this is to the first power to the first power. So since we have linear equations, when we graph them, they're going to be lines. So if I ask you, is 3, 1 a solution, how do you figure that out? Well, you're going to plug it into this system, and it better satisfy both for it to be a solution. So plugging into the first equation, I get 3 plus 1 equals 4. That's true. And plugging it into the second equation, 3 minus 1 is 2, and that's true as well. So is 3 a solution? Yes, because it satisfied both of those equations. Now, will there be another ordered pair that also satisfies that system of equations? Well, let's figure out what opportunities we have for answers. So for a system of linear equations in two variables, exactly one of the following has to be true, and exactly one, so it can't be multiple of these. So one thing we could have is we could have intersecting lines. So that means we would have one solution, and that would be intersecting lines. So let's just draw an example. Here's one line, here's another line, and here's where they intersect. So you get one solution, and there's no way to get another solution out of that. There's one and one only. Well, what other possibilities do we have? Well, we could have no solution. That would be if our lines were parallel, because there's going to be no point that satisfies both of those lines. So that means you would have parallel lines. Well, what other possibility is there if there's one solution and no solution? Well, the last possibility is infinitely many. If you have a line and another one landing right on top of it, then every point on those lines satisfy the other line as well. So that means you have infinitely many solutions, which means you have something called coinciding lines. So when you have infinitely many solutions, you just have one line on top of itself, and so therefore you would have infinitely many solutions. So those are your three possibilities. A little bit more of definition. If a system of two equations and two variables has at least one solution, meaning one or infinitely many, the system is said to be consistent. You're consistent if you have a solution. So you're inconsistent if you have no solution. If you have, back to the first one, if you have only one solution, the system is independent. And then I bet you can guess what this one's going to be. If it's infinitely many solutions, the system is dependent. Alright, so we have three different ways to find a solution to a system of linear equations. We can graph, we can do something called substitution method, and then we can do the addition method. The graphing method is nice, but it doesn't work all the time. It only works when we have nice integer values. So we definitely want to make sure we can do substitution and the addition method. But let's show the graphing method just so you can see how it works. So how are we going to find the solution by graphing? Well, first of all, you're going to graph each line on the same coordinate plane. And then once you find the lines of each one, you're going to find the intersection point. Going to find the intersection point. So we're going to go back to what we learned in the previous chapter on how do we graph lines. So let's look at the first one. We have 5x, this will be my first equation, 5x minus 2y equaling 10. I like to do the cover-up method and find my x-intercept and my y-intercept. So if I cover up my y, because I'm plugging in y being 0, I know my x-intercept is going to be 2. And if I plug in x being 0, I know my y-intercept is going to be negative 5. Now the thing you got to be careful of is if you don't graph this correctly, and when you are connecting your dots, you could be off by just a little bit, and then your intersection point is more of a guessing game. So there's that. So now let's look at the second equation. The second equation is x minus y equals -1. Again, the cover-up method, if y is 0, x is going to equal -1. And when x is 0, y equals +1. So connecting those, we'll see how well I do with finding my intersection point. So looking at my intersection point, it looks like it would be at 4, 5. So it looks like my intersection point is 4, 5. Now, to be sure, we can check and make sure that it satisfies both of those equations. When I plug in a 4 and a 5 here, I get 20 minus 10, which is 10. And when I plug in a 4 and a 5 there, I do get -1. So I did find the correct intersection point. But you got to be very careful how you graph and use a ruler to find out where that intersection point is. So that method is nice, but it doesn't always work, especially if you don't have integers. So we're going to learn the substitution method, and then we're going to learn the addition method. Now, MyMathLab might specify which one they want you to do between substitution and the addition. You can do whatever method you want on the test. I do not specify. So would I want you to know both of them? Definitely. So first things first, solve one of the equations for one variable in terms of the other. I'm going to give you a hint. You want one of them to have a coefficient of 1. So you want a coefficient of 1 for one of the variables. If you don't have a coefficient of 1, don't do this method. Substitute the expression found in step 1 into the other equation. So you're going to plug it into the other equation. Why do you do that? Because then you're going to be left with one variable. And so you can solve for that one variable. Then once you solve for that one variable, you're going to back substitute into the other equations to find the missing variable. And then check to make sure that your solution satisfies all of the original equations. So again, what's great about this section is you can check your answers. So you should know if your answers are right before you turn it in. So let's try some problems and see how this works. Now, solve by substitution. So I'm being specific, but again on the test I will not. Identify the system that has no solution, so just write no solution. But then if you get one with infinitely many solutions, we're going to learn how to write all the answers expressed in set notation. Alright, so we have 3x minus y equaling 8 and y equaling 6x plus 3. We want a coefficient of 1 for one of our variables. Well, the first y up here has a coefficient of -1, so that would be okay. But this one already has a coefficient of 1, and it's already solved for. We know that y equals 6x plus 3, so y is already isolated. So we're going to take whatever y is and plug it into the first equation. So I'm going to get 3x minus, anytime I do a substitution, I better use parentheses because I might have to distribute. So I'm going to plug in 6x plus 3 for y. And as you can see, we're left with just one variable. So now we can solve for that variable. So we need to distribute our minus sign. So we get 3x minus 6x minus 3 equals 8. Then we're going to combine like terms. So we get a 3x minus 6x gives me a negative 3x minus 3 equals 8. Then what do we need to do? We need to add over the 3 to get the variable by itself in a sense. So we're going to add over the 3. And we get negative 3x equals 11. And last thing we need to do is get x by itself, and we do so by dividing by -3. Now remember, you're not allowed to leave a negative in the denominator of a fraction. So move it to the top or put it out in front, but don't leave it in the denominator. So right now it looks like my ordered pair is going to have an x value of -11/3. So then what do I need to do? I need to find the y value. And how do you do that? Well, you plug it in back to one of the original equations. Since it should satisfy both equations, you could plug it into the first or the second. I'm going to choose the second because I already know what y equals. Y is going to equal 6 times x, which is a -11/3, plus 3. So hopefully you practiced with your fractions a little bit. You're not just grabbing a calculator. We're going to multiply straight across. So 6 times -11 is -66. 1 times 3 is 3, and we need to add 3. Well, this reduces nicely. -66 divided by 3 is -22 plus 3. So y is going to equal -19. So my ordered pair as the intersection point is -11/3, comma -19. We could check our answers by plugging back in. So for this example, graphing would not have worked because we could have never figured out -11/3. So definitely understanding how to do another method is the key. So let's look at number 2. Y equals 5x minus 2 and y equals -2x plus 5. We already have y by itself, which means it has a coefficient of 1. So we can plug any y into the other equation. So we'll just take the top one and plug it into the bottom. When I do so, I get 5x minus 2. Again, use parentheses when you're substituting, just in case. Well, we really didn't need those parentheses because there was nothing in front of that y, so we could just have 5x minus 2 equals -2x plus 5. Then we'll get variables on one side and numbers on the other. So we're going to add the 2x over to the left. We'll add the 2 over to the right, and we're going to get 7x equaling 7. So when I divide by 7 to get x by itself, x is going to equal 1. Now don't box that in like I did, just remember that x is 1, so in your ordered pair, you're going to have a 1, comma, something. So what will that something be? Well, you can plug the 1 into the first equation or into the second, it doesn't matter. I'll just plug it into the first. So y is going to equal 5 times 1 minus 2, so y is going to equal 3. Again, you can check that answer by plugging x being 1 and y being 3, x being 1 and y being 3, and it should check out. So that means these two lines intersect at 1, 3. And it's the only time they'll intersect. Alright, so let's look at number 3. Ooh, fractions, right? 2/5 x minus 2/3 y equals 0, and y equals 3/5 x. Since I already have y by itself in that second equation with a coefficient of 1, I'm just going to go ahead and substitute for what y is, and then I'll worry about fractions. So I get 2/5 x minus 2/3 times 3/5 x equals 0. So I'm going to go ahead and multiply straight across, because with multiplying fractions I like it. Just multiplying straight across, I get -6 over 15x equals 0. I do know that it is reducible. 6 over 15, you can reduce both of them by 3, so we get 2/5 x equals 0. And so 2/5 x minus 2/5 x gives me 0 equaling 0. Alright, so when all your variables disappear, this is when you would have infinitely many solutions or no solution. Which one is this? Well, is 0 equaling 0 true? It is. So if you have a true equation when all your variables disappear, that is when you have infinitely many solutions. Now, because it said infinitely many solutions, up here we have to express using set notation. So let's review set notation. Set notation has these little squigglies, and we're going to say the set of all ordered pairs xy. Draw your line down, that means such that. And then the great thing is you can either write the first equation or the second equation, because they're the same one, just written differently. So I'm going to choose the second one because it's a little bit faster to write. So how you read this is a set of all ordered pairs xy such that they have to satisfy y equaling 3/5 x. So we have written all the solutions in one set notation. Alright, let's try 4. So far all of these have already had y by itself. And again, it could be x by itself, but you would not want to get x by itself here because you had a coefficient of 2. You could get y by itself because it does have a coefficient of -1, or you could just go ahead, well, this is already solved for you in the y equals, so we're going to plug in y equaling 2x plus 3. So plugging into the first equation, I get 2x minus, don't forget to use parentheses, 2x plus 3 equals 4. Then we'll distribute our negative, just the negative only, so we get 2x minus 3 equals 4. And what happens when I do 2x minus 2x? They cancel. And I get -3 equaling 4. So all my variables disappeared just like in number 3, but when my variables disappeared, I have a false equation. So this is false, which means those lines are never going to intersect. So if you look back at what we said about those, these lines have to be parallel. So we have parallel lines, which means we have no solution. So your answer is no solution, but I want you to understand what kind of lines you just found. All right, so let's do 5. 2x plus y equaling 7 and 3x plus 2y equaling 12. This is not like any of the other ones because we already had a variable by itself. So we got to figure out which variable should we get by itself. Not the x because it has a coefficient of 2. Not the x here because it has a coefficient of 3. Not this one because it has a coefficient of 2. The only one we want to get by itself would be this y because it has a coefficient of 1. So how do we isolate the y? We're going to subtract over the 2x. So y is going to equal negative 2x plus 7. Or you could write 2x minus, or you could write 7 minus 2x if you'd rather do that. So then what do? We take y equaling and we plug it into the second equation. So we're going to take what y equals and plug it into the second equation. So we get 3x plus 2 parentheses negative 2x plus 7 equals 12. So we'll go ahead and distribute and we get 3x minus 4x plus 14 equals 12. So I'm going to let you finish this problem out, and the answer you should get as an ordered pair is 2, 3. So make sure you can finish that one and get an answer of 2, 3. I'll start doing the addition method in the next video.